Now, given two normed spaces x and y over the same field F, let's give the following definition. Let Lxy denote the set of all bounded and linear operators A, B, whatever you want to call them, from space X into space Y. If X and Y are the same space, then we will just abbreviate this by L of X. Now, so far this is just a set of operators, but because our normed spaces X and Y have plus and alpha times and the norm, there's of course the potential of also equipping Lxy with these structures. So let's look at the following operations. So there's an operation plus between two operators. So A plus B shall be the operator that applied to little x just gives you A of x plus B of x. Now of course note that here is the new plus, whereas this is the good old plus in the space Y. Okay, the other operation that we need is alpha times. So alpha times A shall be the operator that applied to little x just gives you alpha times A of x. And now again, the new operation alpha times is to be seen here, whereas this one is just the alpha times in your space Y. Needless to say that all of these shall hold for all little x's from x. We will see that indeed these new operators A plus B and alpha times A are again elements of Lxy, which means again bounded linear operators. But before we do so, let's also introduce a norm. Okay, and that is easy because we've already done it. So the notation of the operator norm is of course exactly what we're going to use now as our norm in Lxy. Well, let's first check that this is indeed a norm, so we have to check the norm axioms. You still remember the first one? First one says that the norm of something is only then zero if the something is the zero vector. So our norm is the supremum of norm Ax when x has norm 1. But of course that's the case if and only if the norm of Ax is 0 for all x's in x with norm x equals 1, which of course means that all of these Ax's are the zero vector of y. Okay, and now you can just multiply by any little alpha, so that on the left then you get arbitrary x's, and on the right you still have the zero vector. But that's just the definition of A being the zero operator. Let me write it like that. Okay, first norm axiom, check. Let's come to the second axiom of norms. We have to check compatibility with alpha times. So the norm of alpha times A is, by our definition, just the supremum of the norms of this new operator alpha times A when applied to little x's that have norm 1. But now of course you can rewrite this as we defined the operator alpha A to act on little x's. Okay, but from there it's easy to get the little alpha out of this norm, of course as modulus alpha, and then from there in front of the supremum, ending up at modulus alpha times norm of A as we want. Check. For norm property 3, the triangle inequality, let's start with the triangle inequality in Y. So for every x in x, we know that the norm of a plus b applied to x, which is of course the norm of ax plus bx, can be split by triangle inequality in B into norm of ax plus norm of bx, and you get inequality in this direction. Now, because this holds for every x in x, it's still true if we put supremum x with norm equal to 1 in front. So we have to do this in all the other expressions also. So here's our supremum, and then also in front of this sum we put our supremum. But then in this last expression you can of course further improve or increase the gap by putting the supremum separately in front of every term, norm of ax and norm of bx. So each one of them can be maximized first, and then adding the maxima or suprema will of course make the expression even bigger. But then if you read that out, what you see here, you have the norm of a plus b written here, norm of a is here, and norm of b is here, which means we can check property 3, so it's indeed a norm. And by doing so, we have also shown what we promised before, that if a and b are bounded operators, also a plus b is a bounded operator, because the supremum of this expression is not bigger than that norm and that norm added together. So it's again a bounded operator, and also alpha times a is a bounded operator because the corresponding supremum can be given by the norm of a, which is a finite number, times modulus of alpha, which is a finite number. So we can also check these as before. Right, so at this point we arrive at the conclusion that L x comma y is a normed space with the operations as defined above.